Okay, question 9 says sketch the graphs of each of the surfaces described by the equations below. In part A, we're looking at the equation x squared plus z squared is equal to 4. And we saw equations like this back from chapter 12. This equation describes a cylinder. Okay, it describes the cylinder of radius 2 with the y-axis as the axis of the cylinder. Okay, and the reason why again, well, if I think about this equation as describing points in the xz plane. This describes the circle of radius 2 centered at the origin in the xz plane. Okay, now if I take any point on that circle and I fix the x and z coordinates and I let y vary, since this equation is independent of y, right, does not care about the y coordinate, all of those points on this line running parallel to the y-axis that passes through that point will also be included. Okay, so if you do that for all the points on this circle in the xz plane, that's going to give rise to all of the points on this cylinder. Okay, great. So now for part B, the equation is z is equal to x squared. Well, in the xz plane, this describes this parabola. Okay, so in R3, well, here I've just copied that parabola. And by the very same reason as in part A, if I take any point on this parabola in the xz plane, and then I let y vary, and I fix the x and z coordinates, all of those points will also be on our surface because, again, this equation is independent of y. So this gives rise to what we call a parabolic cylinder, right? So you can think of taking this parabola in the xz plane and then just taking copies of it as you run parallel to the y-axis. Okay, so let me jump over here to this graph. Here is our parabolic cylinder, right? This parabolic trough surface. So here's the xz plane, right? X on the horizontal, z on the vertical, and you can see that parabola. And then if you run parallel to the y-axis, right, you get this parabolic cylinder. Cool. All right, so then for C, the equation is y plus z is equal to 4. Okay, and pretty similar here in the yz plane. This describes this line, okay, that has intercepts of 4 along the y-axis and then 4 along the z-axis. So in R3, I've copied that line in the yz plane, and now since this equation is independent of x, this gives rise to a plane that runs parallel to the x-axis. Okay, so if I take any point on this line and I fix the y and the z coordinates, right, and I let x vary, all of these points running parallel to the x-axis will also be included because this equation is independent of x. Also notice, right, going back to the beginning of this section, with our discussion of planes, we recognize this is a plane equation with normal vector 0, 1, 1. Okay, well, very good. So one last thing I want to say here. So here is our parabolic trough where z is equal to x squared. Okay, here is the plane that we just looked at, y plus z is equal to 4. Notice if you look in the yz plane, you see that line, right, as a cross section there, and then since the equation is independent of x, we get this plane that's running parallel to the x-axis. And here's another example, say z is equal to the sine of y. Well, this equation is independent of x, so we should get a surface, right, that runs parallel to the x-axis. And if I look in the yz plane, I should just see, right, our sine curve. And I do, right, there's that sine graph. And then just letting it run parallel to the x-axis gives us this nice sine blanket. Cool. All right, well, that's going to do it for this video. I'll see you next time. Thanks.